Okay, I have 4 problems based on homework that was done. I want to see how well the Mastering Physics homework is working. So 4 typical problems that would come from the assignment that was due today. Everybody did it. Everybody that did it within the last 24 hours. Okay, so we have a 5 Newton force at 37 degrees, a 10 Newton force at 90 degrees. I'm going to get the resultant. I'm not sure everybody knew what I meant by resultant. It means the sum of the forces. And I maybe should have used that terminology. I assumed that the term resultant would have been used in the assignment. We start by sketching a coordinate system with a vector labeled 5 newtons at 37 degrees. We call that force F1. And it should be automatic that the I component of that force is 5 newtons times the cosine of 37 degrees, just analyzing that triangle, and the y component, 5 newtons times the sine of 37 degrees. The second force that I didn't label here's F2. (10 newtons times J, which I also labeled here. We call that F2. Okay, so what we have, if we put the 2 vectors together, is we have that force. We have the 5 Newton cosine 37 degrees times I, 5 Newton sine 37 degrees times J, so that this vector plus this vector, well, the components are have exactly the same effect. The sum of the 2 components have exactly the same effect as the original force. So we can take that original force and cross it out and replace it by its components. So now that our force F1 and our force F2 go together, and it gives this picture where we have the 10 newtons times J here, the F1x here, F1y here, and we add those together. Okay, so it's 5 newtons cosine 37 degrees I plus 5 newtons sine 37 degrees J, and the 10 newtons times J. 5 newtons times sine 37 degrees is about 3 newtons. 5 newtons cosine 37 degrees, very close to 4 newtons. So it's approximately 4 newtons times I, 3 newtons times J. 10 newtons times J adds up to 4 newtons times I, and then 13 newtons times J. Now we could also calculate the magnitude and angle of that resultant, but it wasn't requested. Didn't have a lot of room here, so I didn't do that. Okay, let's separate these 2 problems the way things came out. You got somebody running toward a wall. They run into the wall, exert an average force of -10 kilonewtons times I while in contact with the wall. What force does the wall exert on them? Well, it's going to be +10 kilonewtons times I. Exert the force -10 kilonewtons times I on the wall. The wall exerts a force of +10 kilonewtons times I on you. These forces come about through various compressions. Parts of the wall get compressed and parts of your body get compressed, and then they elastically, more or less, spring back, creating equal and opposite forces. Okay, definition of an inertial reference frame. I really like this definition. I've not seen it defined quite this elegantly, I think. And the idea of an inertial reference frame has been one that's been with me since I was in maybe 9th grade, when I was read something about general relativity or special relativity in an encyclopedia. They talked about an inertial reference frame, but I didn't have a reference for it. We didn't have it in Google. So I asked my teacher, a substitute teacher, who was a retired superintendent, also my backyard neighbor. Taught me a lot of things, but not math. But he's a math guy. So, you know, one of the big schools is named after the guy. Neat guy. And he gave me a pretty good answer. He said, well, you think of it like a coordinate system moving at a constant speed through space, constant velocity. Still didn't grasp it, but just, you know, this concept develops, and I really like this definition within that context. It's one in which Newton's first law works. I use the analogy, or the idea. If you're in a car driving at a constant speed down a road, and you have a level ramp in the car, and you have nice smooth roads, things aren't vibrating, and you have a ball on that ramp, and the ball's at rest, it's going to stay at rest. But as soon as you hit the brake, the ball's going to start moving. So within your reference frame, that ball just spontaneously violated Newton's first law, which says an object at rest is going to remain at rest, an object in motion is going to remain in constant motion unless some force acts on them. Well, you hit the brakes, no force is acting on them. And relative to the road, they're still moving at the same speed, but your car's slowing down. The acceleration of your car makes the frame a non-inertial reference frame. If the ball's slowly moving along the ramp as you're moving down the road and you slam on the brakes, it's a pretty heavy ball, so it just speeds up, goes through your windshield. Things like that don't happen in inertial reference frames unless something makes them move. And nothing made that ball move. Matter of fact, that's why it went through your windshield, because the ball maintained its velocity relative to the road and the car didn't. Okay, well anyhow, there's your inertial reference frame. Another one, you got a mass m at angle phi, mass m on an incline with angle phi with horizontal. First question was, you're going to use a tilted or a level reference frame, and I got various results or answers to that. The general principle, you want to use a tilted reference frame. You want to use a reference frame where whatever's moving or whatever thing you're most interested in is in the x direction, generally, or the y direction, along one of the coordinate axes. And since everything is happening parallel to this plane, as far as motion and so forth, we want to use the tilted reference frame. Excuse me. Okay, so here we have our tilted reference frame and our mg vector, our weight vector mg, at angle phi with respect to the y-axis in the third quadrant. That's a lot to think about. There's an easier way to get the result, but that's what it is and where it is. So you know that your x component is going to be in the negative x direction. Your y component of the mg force is going to be in the negative y direction. Over here, we can say that, looking at this triangle, this component here is adjacent to the angle phi, where mg is your hypotenuse. So you get mg cosine phi times the negative j vector. Now you got to, figure out the triangle, make sure the triangle's oriented right, get the right trigonometric function, and then remember that it's in the negative j direction. You do all that, and you get negative mg cosine phi times j. Okay, that works. And you got to go through a similar set of reasoning steps to get the sign right on this thing and get the right function. You got to look at that triangle and so forth. It's more efficient to use this angle theta from the positive x-axis measured counterclockwise around your vector, because if you do, the x component is always the magnitude times the cosine of this angle, and the y component is always the magnitude times the sine of this angle. This just goes back to the circular definition of trigonometric functions, where the angle is measured from the positive x-axis counterclockwise. Now you don't have to worry about what's positive and what's negative, because it comes out of your calculation. So you don't have the chance to make a mistake. All you got to do is identify this angle correctly as 270 degrees minus phi. And that's a simple step, much simpler than trying to worry about whether it's positive or negative I direction, positive or negative j direction, whether it's a sine or a cosine, looking at the triangle, all that. This cuts through all that. Now I could have said also that this is a vector. The mgx vector would be then this times the I vector, and the mgy vector would be this times the j vector. You don't see the negative signs here, but when you do the cosine and the sine of 270 minus phi, they'll both turn out negative. And it'll be the same numerical result as you got here, but it'll be, and I did something else here, I didn't do something else. This is a vector, this is a vector. Okay. So anyhow, there we have it. If you were programming this in a system, you wouldn't want to have a bunch of decision steps in your program to decide whether it's a sine or a cosine, whether it's a positive or negative I or positive or negative j. If you use this, it's much simpler and more elegant, and gives you the correct solution with fewer chances to make errors. So I definitely recommend it. Doesn't mean it's not important to also look at the triangle, maybe reconcile the two. That's another good way to avoid errors. Do something in two different ways and reconcile them if they don't seem to agree. Okay, we go on. We have a pendulum of length L. I say, okay, let it be 3 meters, but I never use the 3 meters. I just did this all in symbols. And an angle phi, 10 degrees with vertical, and a mass, m, of 2 kilograms. Just in terms of symbols, m, and I never did use the length. If we had the length and the displacement here, then we'd be able to determine the angle and we would have used it. As it is, we didn't need to use it. Okay. We're going to use a level coordinate system because for small angles, the pendulum appears to move back and forth. Now it actually has a little dip in it because it moves along the arc of a circle, since the length of this thing is constant. You know, you get a circle around here, and this is moving along a small arc of the circle. For small angles, you don't have much dip here. So the motion is essentially left and right. Okay, so we assume, okay, well, we start the free body diagram. We know we're going to have the negative mg times j vertically downward. That'll be along the y-axis. And we know that the tension in the string has to be along the length of the string. So the tension's trying to pull the string in, trying to make the string shorter, so this end wants to go that way. So there's the direction of your tension. My color coding probably wasn't too smart here. The tension has a horizontal and a vertical component. If the motion is along the x-axis, then you have vertical equilibrium, so that the y component of your tension has to be equal and opposite to the y component of your gravitational force. So it's got to be plus mgi. This is assuming vertical equilibrium, that is what you get if you have horizontal motion. There's a little more to it, but the y component of the tension will be mgi. The x component of the tension, okay, now there's a gap that I need to fill in here. For small angle, the y component of the tension is approximately equal to the magnitude of the tension. So well, I kind of messed up that word. That messed up word there is angle. I don't think there's any way to redeem it. Small angle implies ty is pretty close to t. Okay, the closer t gets to the vertical axis, the closer the length of this vector gets to the length of this vector. At 10 degrees, there's only maybe a 1% difference in the two lengths. This is the small angle approximation. That's equivalent to saying that the thing moves in the horizontal direction. It doesn't quite move in the horizontal direction. This tension is not quite equal in magnitude to Ty, but we assume they are. And then if you assume this, the x component of the tension, if the magnitude of the tension is mg, then the x component is just mg cosine theta, where theta is this angle, times I. And this angle would be, in this case, 100 degrees. Cosine would be about negative 0.2. And negative 0.1617. Probably 17. Okay, anyhow, you have this tension component. And that's tension, that's a component that causes this thing to be accelerated back toward the equilibrium position. It's important to understand. Now I use the angle theta. You could use the 10 degrees if you wanted to, and that would be your angle phi. And you'd have mg sine phi. Look at that triangle. You see that the sine is the, well, first of all, here's your 10 degree angle here. This is equivalent to this, congruent to this, and it's got a magnitude that's equal to the tension times the sine of phi. So we have this, we have this. Anyhow, there's your diagram, and we'll do a lot more with that. We want to understand the angles and components with that diagram. A mass on an incline at angle phi, I said 6 degrees, but I never used the 6 degrees. We use a tilted coordinate system, as we did in the last example on the previous board, the fourth problem on the quiz. We have mg down here, and free body diagram here. mg down, there's going to be a normal force here. We demonstrated that by, I guess it's worth taking a second to demonstrate it. Okay, if this little orange piece of chalk is a lot more massive, gravity's going to pull down and the meter stick's going to bend. When I release it, will the chalk go straight up? No, chalk goes that way, and it left at a perpendicular to the meter stick. Maybe this ramp bends a little bit and pushes it causes a force perpendicular to the ramp on this ball, and maybe the ball just compresses it. The compressive force is still the reaction, the elastic reaction, those compressive forces still exert a force perpendicular to the incline. So the normal force is perpendicular to the incline. Because you have equilibrium in the y direction, equilibrium perpendicular to the incline, that normal force has to be equal and opposite to the y component of your gravity. The y component of your gravity is mg cosine phi times negative j, or mg sine of 270 degrees plus phi, the angle theta, measured from the positive x-axis, times j. And mgx is either mg sine phi times I, and that's the force that accelerates you down the incline if there's no friction. And that could also be written mg cosine of 270 degrees plus phi by this, and you can do this without thinking much. This requires more thinking, but also there's intuition involved, so both ways of looking at it are valid. Okay, well, there's that. Now we go to a situation that's not like anything anybody would have seen on the Mastering Physics, because it involves a rotating beam, but since that's what we started the course with, it should be a familiar phenomenon. Okay, so let's assume we have a mass M1 by this, designated by this orange dot, M1 of 200 grams at 30 centimeters from the axis of rotation, an M2 of 10, of also 200 grams, but only 10 centimeters. So these are equal masses, but at different distances from the center. The question is, how much force does it take to accelerate each of these masses if the beam is accelerating with angular acceleration of 1 radian per second squared? Now, we are familiar now with the fact that a radian of angular displacement is equivalent to a displacement along the arc of magnitude equal to the radius. So that a radian per second squared becomes a radius per second squared. So for the mass M1 has acceleration A1, which is 30 centimeters per second squared, times which is equal to 0.3 meters per second squared. Now, the beam has the same acceleration, angular acceleration, but the acceleration of this particle is going to only be 10 centimeters per second squared, because it's moving along a circle of radius 10 centimeters, and a radian is only 10 centimeters on that circle. So we have a 10 centimeter per second squared acceleration, 0.1 meter per second squared. It should be clear that both masses are accelerated in the direction perpendicular to the beam, wherever the beam has to be. They're moving only in that direction. They're moving on that circle. The motion is tangent to the circle they're moving on. Each is moving on its own circle, tangent to that circle. So, F1, the force you need to exert here, has a magnitude of M1 times A1. Well, M1 is 0.2 kilograms, A1 is 0.3 meters per second squared. You get 0.06 newtons. And F2 is M2A2. Using Newton's second law, you get 0.02 newtons. So in accelerating this, whatever force or torque you're using to accelerate it, it has to provide more force on this mass than on this mass. And this is kind of an important insight that will become more important in a few weeks when we start looking at moment of inertia, something you learn to calculate in calculus class by integration and so forth, but something that you probably, unless you've dealt with it before, really didn't have much of a feel for. And the point being that all the particles in this beam, which the beam you have also has a mass of about 200 grams. But those masses are continuously distributed from one end to the other through a bunch of very almost infinitesimal particles. Mathematically treatable as infinitesimal particles. Okay, well, that complicates things when you're trying to do Newton's second law for rotating objects. Okay, every mass, every particle has a different distance from the axis, requires a different force, and that has all kinds of implications that we'll examine when we get there. Just getting used to this one example here. And it's a very straightforward application of Newton's second law, and a very straightforward application of definition of a radian and the equivalence between angular and linear acceleration that we've dealt with to some extent by this point in the course. Okay, so that's kind of it for now.